Welcome to this video tutorial on impulses. Firstly, let's define impulse. It is usually represented by the variable j for when it is a scalar, or for when it's a vector, j with our vector notation, which I shall use a line. When considering scalars, our impulse j is going to be equal to the average force multiplied by a change in time. But then this is also going to be equal to our mass multiplied by a change in speed. And as you can see, this is equal to the change in momentum. This means that we can work out the impulse in two different ways. And then we can solve questions by solving for one of these variables if we know the other three. If we're considering vectors, then the formula is very similar. We have once again the average force, but this time considering it as a vector, multiplied by the change in time. Or this is also equal to the mass multiplied by the change in velocity, which is once again the change in momentum as a vector. Let's also consider the units. As you can see from our formula, if we use dimensional analysis, we can see we have a force, which has the units newtons, multiplied by a time, which has the units seconds. And so we get the interesting unit of Newton seconds. But also consider that it is also exactly equal to a mass, which has the units kilograms, multiplied by a change in speed, which has the units meters per second. And so for our impulse, we can use the units Newton seconds or kilogram meters per second, which has the exact units of momentum itself. As impulse, if you see, is just defining a change in momentum. In this tutorial, I'll be using the units Newton seconds. As we learned in a previous tutorial, momentum is conserved. This means that the momentum before and after a collision is the same. Our impulse is equal to the change in momentum. And so what does that mean for its conservation? Well, if you think about it, if an impulse is given to an object that changes the momentum from before to after a collision, then this means that momentum isn't conserved. In order to conserve momentum, there must be an equal magnitude impulse applied in the opposite direction to change another object's momentum. Meaning that if one object's momentum is increased by an impulse, then in order to conserve the total momentum, another object's momentum must be decreased using an equal but opposite impulse. Therefore, impulses come in pairs, meaning that one impulse is equal in magnitude to another impulse, but opposite in direction. One really useful thing about the impulse is it can be calculated from FT plots, where in this case we're going to have the force with the units in newtons going in the y direction, the origin here, and then down here we have the time with the units seconds. If we consider a square in the middle of this plot, where we can trace it down to the axes, then here in the middle we have an area which I will call AFT, which just stands for the area of a force time diagram. As you can see here, we'll have a force 2 and a force 1, and then a time 1 and a time 2. Now we know from the top of this page that the impulse J is equal to the average force times the change in time. As you can see, the impulse is equal to a force multiplied by a time. If we wanted to work out the area of this square, then we would have two quantities. We would have a force, F2 minus F1, and a time, T2 minus T1. As you can see, this area, Ft, is equal to a force times a time. And therefore, we can actually say that when looking at a graph, we can ignore this average force, as we can actually see the force at every point in time. The impulse is actually equal to the area of a force time graph. Let's move on to an animated example of this. For this system, we need to find the speed of the ball as it hits the ground, and then use this to find the impulse required to bring the ball to rest. Later on in the question, we're then going to compare this to the initial impulse. And so we'll have a final impulse up here and an initial impulse down here, and then we will compare the two to see if it was conserved. But firstly, we need to solve this simple Suvat equation. We need the Suvat equation that does not have time, which will be v squared equals u squared plus 2as. And now we make v the subject by taking the square root of u squared plus 2as, which, when we sub our values in, u is 0, this is just 2 multiplied by a, which is 0.69 times g, the acceleration due to gravity on Earth, which is 9.81, multiplied by s, 3.6. When subbing this all into your calculator, you will find that v, the final speed just before the ball hits the ground, is going to be, to two significant figures, 7.0 meters per second. And next we need to find the impulse required to bring the ball to rest. We know that our impulse, J, is equal to F times T, or the average force times the change in time, or our alternate definition, which is m delta v, or the change in momentum. We know that delta v can also be called the final speed minus the initial speed. And now we need to decide on our speeds. Our final speed should be 0, as we're trying to bring the ball from rest from its final speed just before it hits the ground. So therefore, Vf is 0. Now let's define our initial speed. In this Suvat equation, we defined the downwards direction to be positive. As you can see, our 3.6 meters from the top to the bottom of the apparatus is a positive value, even when acting downwards. We're going to define this as downwards, minus 7. And this does make sense, because we've now defined the upwards direction to be positive. This means that we can now sub our values in to get our impulse, which is going to be m, which is the mass, which is 10, multiplied by the final speed, which is 0, minus 7, which is 10 multiplied by 7, which is 70 Newton seconds for our impulse. And now for this part of the question, as we defined upwards to be positive, this means that this impulse is also positive and so also acts in the upwards direction. And this makes sense, because if you think about what is applying the impulse, it is the floor applying an impulse upwards to the ball to slow it down as it approaches the floor. Let's move on to our next question. We're now going to try and calculate the impulse required to speed up the ball from its initial position at the top of the apparatus as it free falls down to the floor. How do we do this? Well, we know that the impulse J is going to be equal to the area of an FT graph, which conveniently we have here. But what area are we trying to consider? We know that if we want to find the impulse that was applied to the ball as it fell, as the question states, then we need to only consider the area of the graph that applies when the ball is free falling. And this is going to be the only part of the graph where the force is uninterrupted, because only the force of gravity applies. So therefore, you can see that this sort of region here, we have a pretty much uninterrupted force, which applies for roughly a second. And so this to me looks like the time we should be considering. When calculating the area, we should draw a dotted line across the f equals 0 point, as this is where we're going to now calculate the area from. And as you can see, it's going to be a negative area. As you can see, the negative forces at this time imply the downwards gravitational force acting on the ball. This data has been extracted directly from the program I used to make this animation. That this is why we actually switched our definition of the positive direction in the question above to make it consistent with this question. Let's calculate our area. If we forget the fact that there is a slight variation in force over the second at the bottom here, if we call this roughly what it should be, which is, if we draw our dotted line across, somewhere around the region of 65, 67.5, then we get that the impulse is equal to the area, which is equal to minus 67.5 multiplied by our change in time, which, as you can see, is on the most part 1 second. And this means that our impulse here is going to be approximately 67.5 Newton seconds. I'm now going to label this the initial, and the one up here the final impulse. Now what does this show? This shows, in order to get the ball moving from a stationary point on top of the apparatus, when it free falls, an impulse of 67.5 Newton seconds was applied by gravity to the ball, which got it moving to the floor. And then when the floor wanted to stop it, at the bottom here, an impulse of 70 Newton seconds was applied to stop the ball. And so, as you can see, the impulse required to get the ball to a certain speed and the impulse required to stop the ball was exactly the same, in magnitude at least. And what does this also show? As you can see, the magnitudes are incredibly similar, and any variation is likely due to the fact that our calculation of this area was not exact. We made an assumption here that the square was slightly smaller than it actually was. We also didn't read off our values too correctly either. And so it is likely that if this was done computationally in these perfect examples, then these values would have been the same. Let's play the animation and move on to some more typical written questions. Question 1. Two balls collide. The impulse of the first ball on the second is J12 as a vector, and the second on the first is J21 as a vector, where these vectors respectively are 10x hat minus 5y hat Newton seconds and minus 10x hat plus 5y hat Newton seconds. And we need to find the change of velocity of each ball if they both have a mass of 1 kilogram. Firstly, we need to remember that in general, the impulse is equal to the average force times the change in time which is also equal to the mass multiplied by the change in speed. And once again, for vectors, we place our vectors as such. Let's write out our equation for our first impulse j12. J as a vector 1, 2 is going to be equal to, now as you can see there is no mention of forces or times in this question, so we're just going to ignore this middle part and use the other parts. And this is going to be equal to m times the change in velocity. But which balls change in velocity and which balls mass? J12 is the impulse of the first ball acting on the second, which means that the ball that's going to feel the effects of this impulse is going to be the second ball. And so we're going to say m2 and velocity 2. And so likewise, for the other half of the question, J21 is going to be the second ball acting on the first, which means that this equation will have m1 multiplied by delta v1. In both of these we need to calculate the change in velocity, and so we simply make delta v2 the subject. Delta v2 will be j12 over m2, and here delta v1 will be equal to j21 over m1. Let's sub in our values. We know that j12 is 10x hat minus 5y hat, all divided by m2. Now both balls have a mass of 1 kilogram, and so therefore we have 1. And then in this question, j21 is minus 10x hat plus 5y hat for j21 divided by the mass, which is 1 kilogram. And so we get the change in velocity for ball 2 is 10x hat minus 5y hat meters per second, and the change in v1 is going to be equal to minus 10x hat plus 5y hat meters per second. And this will make sense because, as you can see, the impulses acting on each ball are equal in magnitude but opposite to each other, and so it makes sense that if they have the same masses, so with their velocities. Let's move on to question 2. A ball is instant on a soft wall. The ball has a speed of 5 meters per second and weighs 2 kilograms. Let's draw this in the diagram. Here we have our soft wall, which is drawn like this, and we have a ball rolling towards it with a mass of 2 kilograms and a speed of 5 meters per second. Figure 1 shows the force time plot of the reaction force of the wall, where a positive force is acting in the opposite direction to the initial direction of motion of the ball. The initial direction of the ball is acting in the direction drawn here, and so therefore our positive direction is acting in the other direction. And so this is going to be our positive direction. We need to approximate the final speed of the ball after the 2 seconds of interaction. So how are we going to do this? We know that for grass, our impulse is equal to the area of an FT plot. We also know our impulse is equal to the mass times the change in speed, meaning that if we can find out the area, then we can find the change in speed and compare that to our initial speed. As you can see, we only need to approximate the final speed, which means we only need to approximate the area. I think the best way to do this is to assume that this nice curve that we have is approximately a triangle that looks something like this. This means that our impulse is going to be equal to the area of the triangle, which is 1/2, times the base, which is 1 second, going from 0.5 to 1.5, multiplied by the height, which is 4 newtons. And therefore, our impulse is going to be 1/2 multiplied by 1 multiplied by 4, which is 2 Newton seconds. And this is positive, notice, which means it's acting in the opposing direction to our initial velocity. We know then that this 2 Newton seconds, which is equal to J, is also equal to our mass multiplied by our change in speed, which is also equal to our mass multiplied by our final speed minus our initial speed. Let's define these really quick. Our final speed is what we want to find out, as said in the question, and our initial speed is 5 meters per second. But look which way we defined our positive direction. It is going in this direction, whilst our initial speed is going in the opposite direction, meaning that this is actually -5 for our initial speed. If we rearrange this equation with J equals m multiplied by Vf minus Vi, we get that J is equal to mVf minus mVi. We can then get that mVf is equal to J plus mVi. And then we can divide through to get Vf is equal to J plus mVi, all divided by m. And now when we sub our values in, we get the impulse, which is 2, plus m, which is 2 kilograms up here, multiplied by Vi, our initial speed, which is -5, all divided by our mass, which is once again 2 kilograms, and then we get that our final speed is 4 meters per second. And so what does this show? It shows that our initial and our final velocity are actually acting in the same direction, -5 and -4 meters per second, which means that after hitting the ball has still got a speed of 4 meters per second in the same direction, which means it's likely that the wall collapsed as the ball rolled through it. Thank you for watching this video tutorial. Visit my website coherentphysics.com for many examples with fully worked solutions.